3,000 meters beneath the surface of the Pacific Ocean, where sunlight has not penetrated for millions of years, a mother clings to a rocky outcrop in total darkness. She hasn't eaten in over a year. Her body, once vibrant and powerful, has begun to waste away, but she cannot leave. Beneath her 8 arms, protected by her weakening body, cluster 60 translucent eggs, each containing a life that will never know her. She shifts slightly, her suction cups gripping the stone, and through the inky black water, something stirs. A predator, drawn by the scent of vulnerability. She tenses, ready to fight with the last reserves of strength in her dying body. This is the octopus, not the creature you think you know from tide pools or aquarium tanks. This is something far older, far stranger, and infinitely more remarkable. A being that survived the death of the dinosaurs, that outlasted 96% of life on Earth, that evolved intelligence so alien it might as well have come from another planet. Welcome to the abyss. Welcome to the world of the deep-sea octopus. The story begins not in the crushing depths, but in the distant past, in a world that would be unrecognizable to us today. 330 million years ago, long before the first dinosaur drew breath, long before the continents assumed their current shapes, a strange creature drifted through the warm, shallow seas of what would one day become Montana. It had 10 arms, not 8. Each arm was lined with suckers in perfect rows, and within its torpedo-shaped body, tucked between masses of muscle tissue, sat a sac of ink ready to cloud the water at the first sign of danger. This was Calypsomopodibidon, the oldest known ancestor of the modern octopus, and its discovery rewrote everything scientists thought they knew about cephalopod evolution. The fossil, barely 5 inches long, lay forgotten in a museum drawer for decades. It had been donated to the Royal Ontario Museum in Canada in 1988, just another specimen among thousands, its significance hidden beneath layers of ancient stone. But when paleontologist Christopher Whalen finally examined it in detail, he realized what he was holding. The creature was perfectly preserved, so well preserved that individual suckers were still visible on its arms, that the remnants of its ink sac could be identified, that its very muscle structure remained intact after more than 300 million years. This was impossible. Soft-bodied creatures almost never fossilize. They decompose too quickly, their bodies too fragile to withstand the slow transformation into stone. Yet here it was, a ghost from an impossible age, pushing the known ancestry of octopuses back by 82 million years. The seas of the Carboniferous period were nothing like our oceans today. They were warmer, shallower, teeming with lifeforms that seem alien to modern eyes. Trilobites scuttled across the seafloor, massive predatory fish, armored in fixed scales, hunted through forests of strange corals. And somewhere in this primordial ecosystem, the ancestors of the octopus were learning to survive. They were not apex predators. They had no shells to protect them like their cousins, the ammonites, whose spiral shells filled the ancient seas. They had no size advantage, no venomous spines, no armor plating. What they had was something far more valuable. They had adaptability. Evolution is not a process of improvement, it is a process of survival. The creatures that endure are not necessarily the strongest or the fastest or the most heavily armored. They are the ones that can change, that can occupy new ecological niches, that can survive when the world turns hostile. And the world turned hostile many times. During the Devonian period, around 372 million years ago, the oceans lost their oxygen in catastrophic pulses called the Kellwasser events. Reef-building organisms died en masse. Ancient relatives of squid and octopuses called goniotites, creatures with beautiful spiral shells, were devastated. But some survived. Some adapted to the low oxygen conditions, developing new metabolic strategies, new ways of processing the scarce oxygen remaining in the poisoned seas. Then came the Great Dying. 252 million years ago, the Earth experienced the most catastrophic extinction event in its history, the Permian Triassic extinction. Volcanic eruptions on a scale impossible to comprehend flooded the atmosphere with greenhouse gases. Global temperatures soared, the oceans became acidic, oxygen depleted dead zones. 96% of all marine species vanished. Forests died and did not recover for 10 million years. Insects, which had survived every previous catastrophe, died in unprecedented numbers. The world became a graveyard. But octopus ancestors survived. While their shelled cousins, the ammonites, were nearly wiped out, the soft-bodied cephalopods endured. Why? Because they had already begun to lose their shells. The external shells that protected so many marine creatures also became a liability. Shells require calcium carbonate to build, and in acidic oceans, calcium carbonate dissolves. Shells are heavy, requiring energy to carry, and in low-oxygen waters, energy is the most precious resource. Shells limit movement, and when the world is ending, the ability to move, to flee, to find new habitats becomes the difference between extinction and survival. The octopus ancestors chose a different path. They internalized their shells, reducing them to small remnants, or lost them entirely. They became creatures of pure muscle, of flexibility, of speed. They could squeeze into crevices that shelled animals could never access. They could escape predators with bursts of jet propulsion. They could inhabit environments that would kill their more rigid cousins. And as the world recovered from each mass extinction, as new ecosystems emerged from the ruins of the old, the octopuses were there, adapting, diversifying, colonizing every conceivable marine habitat, from warm tropical reefs to the frozen waters of the Arctic, from shallow tide pools to the deepest trenches on Earth. By 66 million years ago, when an asteroid struck the Yucatan Peninsula and ended the age of dinosaurs, octopuses were already well established in the world's oceans. The impact winter that followed, the massive tsunamis, the global firestorms, the collapse of food chains, all of this decimated life on Earth, but octopuses, with their flexible diets, their ability to survive in low-oxygen conditions, their adaptability to temperature changes, endured once again. While the great marine reptiles vanished, while countless fish species went extinct, the octopus line continued, evolving, changing, preparing for its conquest of the ultimate frontier, the deep sea. Imagine descending into the ocean. The sunlight fades quickly. At 200 meters, you enter the twilight zone, where only the faintest blue light penetrates. At 1,000 meters, you are in complete darkness. The pressure has increased to 100 times what you experience at the surface. At 2,000 meters, 200 atmospheres. At 3,000 meters, 300 atmospheres. The weight of the entire ocean presses down with a force that would instantly crush any human, that would compress our bodies to the size of a softball, that would collapse our lungs and rupture every cell in our bodies. The temperature hovers just above freezing. There is no light, no warmth, no easy access to food. This is where the deep-sea octopus lives. This is home. The adaptations required to survive in this environment are so extreme, so alien, that deep-sea octopuses seem like creatures from another world. Consider the pressure. 3,000 meters down, the water presses against every surface with a force of over 4,000 pounds per square inch. How does any living thing withstand that? The answer lies in chemistry and architecture. Deep-sea creatures have no air pockets in their bodies. Air compresses under pressure, which is why human divers must worry about decompression sickness, about nitrogen bubbles forming in their blood. But octopuses have no lungs, no swim bladders, no rigid gas-filled spaces. Their bodies are made almost entirely of muscle, water, and other incompressible tissues. The water inside their cells is at the same pressure as the water outside, creating equilibrium. But pressure does more than crush. It also affects the shape and function of proteins, the molecular machines that perform nearly every function in living cells. Under extreme pressure, proteins can become distorted, folding incorrectly, losing their ability to catalyze reactions or transport molecules. Deep-sea organisms solve this problem with piezolites, small organic molecules that bind to water and create space around proteins, preventing the pressure from crushing them into uselessness. The deeper an animal lives, the more piezolites it accumulates. One particular piezolyte, trimethylamine N oxide, or TMAO, is so concentrated in deep-sea fish that it gives them their characteristic fishy smell. Octopuses use similar chemical strategies, their bodies saturated with protective compounds that most surface-dwelling creatures would find toxic. Then there is the darkness. At depths below 1,000 meters, no sunlight penetrates. The only light comes from bioluminescence, the cold chemical glow produced by living organisms. In this perpetual night, eyes become either enormous or useless. The Dumbo octopus, one of the deepest dwelling species, has eyes the size of its brain, massive orbs capable of detecting the faintest bioluminescent flicker in the darkness. These eyes are not like human eyes. They have evolved independently, arriving at a similar solution, a camera-like eye with a lens and retina, through completely different evolutionary pathways. This is convergent evolution at its most striking. Two completely unrelated lineages, vertebrates and cephalopods. But octopuses do not rely on vision alone. Their 8 arms are sensory organs of extraordinary sophistication. Each suction cup contains thousands of chemoreceptors, cells that can taste and smell the water. They can detect the chemical signature of prey or predators from meters away. The arms are also lined with touch receptors, so sensitive they can detect the texture of objects, the movement of water currents, the approach of another creature even in complete darkness. And here is where the octopus becomes truly alien. Each arm has its own nervous system, its own cluster of neurons, its own mini-brain. An octopus has approximately 500 million neurons in its body. 2/3 of those neurons are not in the central brain, but distributed throughout its 8 arms. Each arm can think, can problem solve, can act independently. If you sever an octopus's arm, it does not simply die. It continues to move, continues to respond to stimuli, continues to search for food. It will even avoid the mouth of its own species if it detects octopus flesh on its chemoreceptors, suggesting that the arm retains some memory, some fragment of identity even when separated from the body. This is decentralized intelligence, a nervous system more like a computer network than a centralized brain. The octopus does not command its arms like a general commanding troops, it delegates. The central brain sets goals, find food, escape danger, and the arms figure out how to achieve those goals on their own. This allows the octopus to process an enormous amount of sensory information simultaneously, to multitask in ways that animals with centralized nervous systems cannot. The deep-sea octopus's body is a marvel of soft robotics. It has no skeleton, no rigid structures except for a hard beak hidden in the center of its arms where they meet. This beak is the only part of the octopus that cannot squeeze through narrow openings, and the rest of the animal can deform to fit through any gap larger than that beak. A 100-pound giant Pacific octopus can squeeze through a hole the size of an orange. Smaller deep-sea species can slip through cracks barely wider than a coin. This flexibility is possible because octopus muscle tissue is unlike almost any other muscle on Earth. It is not organized into the simple fibers that make up human muscles. Instead, it is arranged in a 3-dimensional lattice that can extend, contract, twist, and bend in any direction. The arms contain no bones, no joints, yet they can be stiffened or relaxed at will, allowing the octopus to create temporary skeletal structures where needed, to reach into crevices, to manipulate objects with a dexterity that rivals human hands, despite having no fingers. The most bizarre adaptation may be the octopus's copper-based blood. Most animals on Earth use hemoglobin, an iron-based molecule, to transport oxygen in their blood. This gives vertebrate blood its red color. But octopuses and other cephalopods use hemocyanin, a copper-based molecule that turns blood blue when oxygenated. Hemocyanin is less efficient than hemoglobin